Hello MS1s, welcome to Lecture 9, Hemodynamics. We are continuing our pivot from the pump to the pipes with the study of blood flow in vessels. Here are your learning outcomes for this lesson. What is meant by the term hemodynamics? Well, of course, the root word hemo comes from blood, dynamics means movement. Hemodynamics is concerned with the physical properties of blood and its movement through vessels. Now, the flow of blood through vessels, especially very narrow ones like capillaries, has several unique properties, in part because blood is not an ideal fluid. Unlike water, blood is a thick suspension of cells, and the plasma is a viscous solution of dissolved protein. And so blood has certain peculiar non-ideal properties that we need to emphasize. The flow of fluid through tubes was first studied by Isaac Newton about 300 years ago. And Newton recognized that fluids can flow through tubes in two different ways. Laminar, or streamline flow, occurs when the fluid flows smoothly in concentric layers called lamina. Laminar flow is very efficient energetically and is silent. Turbulent flow occurs when the lamina break down into chaotic eddy currents that move randomly in all directions. Turbulent flow is inefficient energetically and noisy because some of the energy driving turbulent flow is given up as heat and sound. About 200 years later, a guy named Osborne Reynolds became interested in Newton's work on fluid flow, and he did a simple experiment. He set up a container of water with a narrow glass tube that he could observe with a magnifying glass the flow of fluid. And to measure the flow of fluid, he injected a dye into the tube through a catheter placed at different distances from the wall of the tube. And when the dye was injected, he saw that it moved in an axial column that didn't mix with the rest of the fluid. He also noticed that the velocity of flow depended on where the dye was injected. The dye moved faster when infused into the center of the tube and slowest when injected near the wall. So confirming Newton, Reynolds showed that fluid flows in concentric layers and that the lamina in the center of the tube moved fastest. Reynolds went on to study the effects of flow velocity and the character of flow. He increased the flow velocity simply by adding more fluid to the container to raise the hydrostatic pressure head, the driving force pushing fluid out through the glass tube. As you might expect, Reynolds found that the rate of flow in the tube increased in direct proportion to the driving force. In other words, the pressure gradient. This is simply Darcy's law of force flow. Remember its application in electricity, where delta V equals IR, Ohm's law. So if a weak pressure gradient was applied in this range, flow was slower and laminar in character. With increasing pressure, flow rate increased as expected up until a critical velocity was reached. At this point here, flow changed from laminar to turbulent. If some energy is given up as heat and sound, less energy will be available to drive the fluid flow. So beyond the critical velocity, extra energy must be applied to produce faster flow. So when flow is turbulent, it increases in proportion to the square root of pressure. Now, Reynolds methodically examined the various factors that cause laminar flow to take on turbulent character. In other words, the factors that determine the critical velocity threshold. And Reynolds expressed these factors in a value he egocentrically called Reynolds number, or RE. And we can think of Reynolds number as the tendency to take on turbulent character. As you might expect, Reynolds number increases in proportion to the flow velocity, the diameter of the tube, and the density of the fluid. It increases in inverse proportion to the viscosity of the fluid. And when this value exceeds the magic number of 2000, flow tends to take on turbulent character, although it should be kept in mind that this transition is somewhat gradual. Now, in the human circulation, Reynolds number rarely exceeds 2000, so laminar flow is the general rule throughout the circulation. However, there are a few special places where flow can begin to take on some turbulent character, especially in the pulsatile flow during systole. We see this in certain regions of the ventricular cavity, the aorta, and the pulmonary artery. Why? These structures have a large diameter and a fast velocity. This is illustrated in this simulation of pulsatile flow in a normal human carotid artery. At the bifurcation of this artery, there's an abrupt deflection of blood into two different paths, and we can see some turbulent character where there are chaotic eddy currents formed right at the bifurcation. Keep in mind that when turbulence occurs, it generates vibrations in the vessel's wall, and these sounds can be heard with the stethoscope as murmurs. Remember, turbulence can occur when flow velocity is unusually high, for example, across a narrow opening of a heart valve or a blood vessel. There are also several pathological circumstances in which blood flow can take on turbulent character. For example, in anemia, there is a reduction in the number of red blood cells that are suspended in the plasma, and the viscosity of the blood will decrease. And since viscosity is decreasing, Reynolds number is increasing. And if it rises above 2000, flow can take on turbulent character. In this case, it's called a hemic murmur. Turbulent flow can also occur across a narrowed heart valve, a stenotic valve. In this case, the diameter of the outlet port is reduced. However, this will force blood to jet across the narrowed opening at much greater velocity, and we can see a net increase in Reynolds number and a cardiac murmur. Another circumstance in which blood flow can take on turbulent character and emit sound is seen in atherosclerosis, where fatty plaques develop on the inner surface of the blood vessel, and this narrowing of the vessel lumen causes blood to jet across the narrowing at high velocity. It can become turbulent and produce a sound. When blood flow through a vessel, usually an artery, emits sound, we call that sound a bruit, B-R-U-I-T. Another example of something similar is seen whenever you measure blood pressure with a sphygmomanometer. You hear the so-called Korotkov sounds. Let's go through that. Suppose we want to measure arterial blood pressure in a patient. We wrap an inflatable cuff around the patient's arm, usually right above the elbow, and we inflate the cuff so that the pressure exerted on the arm exceeds about 140, 150. Because the pressure in the cuff exceeds the maximal pressure in the artery is compressed during both systole and diastole. We call this extravascular compression. And if the extravascular compression exceeds the arterial pressure, there will be no flow, no sound. Let's call that point A. Now the pressure in the cuff is gradually released, and as the pressure in the cuff drops, we reach a point where the cuff pressure, the extravascular compression, drops just below the pressure in the artery during systole. Let's call that point B. At that point, the arterial pressure is just enough to open up a narrow passageway for the blood to jet across at high velocity in a turbulent manner, producing a high-pitched snap, snap. And at that point, we record systolic blood pressure. Notice that during diastole, the pressure drops below the cuff pressure and there's no blood flow. We continue to release the pressure in the cuff gradually, and the snap, snap sounds will become more muted and dull, and at some point these Korotkov sounds will disappear. And that occurs at point C, where the pressure in the cuff drops below the pressure in the artery during systole and during diastole. The blood flows freely through the artery, there is no jetting across a narrowed constriction, and the Korotkov sounds disappear. The point at which they disappear we record as diastolic pressure right here. So as the pressure in the cuff is gradually released, the point at which we hear a high-pitched snap, snap, snap is recorded as systole. The point at which the sounds become muted and dull, finally you'll hear a thud, thud, the sounds will disappear, and at that point we record diastolic. Let's take a brief detour and consider the types of bleeding. Suppose you encounter a patient that is bleeding. How do you know if it's bleeding from an artery, a vein, or capillary? Well, you know that arterial blood is under high pressure, and that pressure is pulsatile. You also know that arterial blood is coming directly from the lungs, so it will be well oxygenated and therefore bright red in color. So an arterial bleed will be profuse and pulsatile. In fact, it will sometimes squirt several feet out in the air, and it will be bright red in color and difficult to stop because it is under high pressure. How about a venous bleed? Well, venous pressures are typically only 10 or 12 millimeters mercury, low pressure. So if a vein is lacerated, we typically see slow, steady flow, and the coloration of the blood will be slightly darker because the vein carries deoxygenated blood from the tissues. The venous bleed will be easier to stop because it's under low pressure. And finally, a capillary bleed will be seen as a slow ooze. It's the easiest to stop. This would be laceration of the superficial dermis with oozing of both blood and lymphatic fluid. Now let's consider the extravascular compression provided by tourniquets. Recall that the veins not only carry blood under low pressure, but they run very superficially. They're very close to the surface of the skin. And so if a tourniquet is applied as you would in a venous blood draw, the superficial veins under low pressure will be collapsed, the arteries lying close to the bone will not, and the blood carried back toward the heart will be blocked, and these veins will dilate under the back pressure, and these veins will be easier to visualize and puncture. How about an arterial bleed? Blood carried by the arteries is under high pulsatile pressure, so a deep laceration that severs an artery will require a very strong tourniquet that provides severe extravascular compression to overcome the 130 millimeter systolic blood pressure. We've already discussed Newton and Reynolds. Similar experiments were carried out by the French physiologist Jean-Léonard Marie Poiseuille. He lived about 165 years ago. He's the guy, by the way, that suggested using the mercury manometer for measurement of blood pressure. That's where we get the millimeters mercury. Like Newton and Reynolds, he liked to tinker around with fluids flowing through tubes, and he refined Darcy's law of force flow, and he showed that blood flow depended on the driving force, in other words, the pressure gradient, the viscosity of the fluid, the geometry of the tube. And he developed this equation, which is now called Poiseuille's law. Poiseuille was a brilliant experimentalist, but I think we can derive Poiseuille's law just from basic intuition. We have a pairing of two identical tubes, one with a larger pressure. Which tube will have the greater flow? Well, it's pretty obvious. This top tube, right? Here we have the same pressure gradient, but one tube has a wide bore and the other has a narrow bore. In which tube will the flow be faster? It's pretty obvious. The bottom tube, right? We have an identical pressure gradient, but we're pushing it through a short tube versus a long tube. In which tube would flow be faster? The top tube. And finally, we have two identical tubes. In one, we're pushing water through it, and the other, we're pushing molasses. In which tube would flow be faster? Well, the top tube. So there you go. You've just derived Poiseuille's law. And remember that Poiseuille's law was built on a framework of Darcy's law of force flow. That is, that flow, often denoted as Q, is proportional to the driving force, that is the pressure gradient across the tube, and inversely proportional to the resistance that impedes flow. In other words, the frictional resistance along the length of the tube. So Poiseuille recognized, again, that flow is proportional to the pressure gradient, the driving force. It's inversely proportional to the viscosity. Remember the molasses versus water experiment. And it is dependent on a geometry term that is largely dominated by the resistance of the vessel. Notice that the resistance term is to the fourth power. And whenever you have any mathematical expression in which a term is raised to the fourth power, that term will tend to dominate the equation. So this geometry term includes the radius, the fourth power, divided by the length. Recall, we all agreed that as the length of the tube increases, the flow through it will decrease, and it's because of greater resistance. And finally, there's a constant that Poiseuille had to add to make all the math work out. By simply arranging terms, we can come up with an expression for resistance. Let's see if it makes sense. The resistance would increase if the fluid were more viscous, or if the tube were longer, and it would decrease if the tube were wider. So by far the most influential factor in determining the resistance of a tube is the radius, because it's to the fourth power. So remember that arterioles have a small radius, and this radius can be altered by constriction of their smooth muscle coat under the influence of the sympathetic vasoconstrictor fibers. Poiseuille's law tells us that if vasoconstriction results in a decrease of the lumen diameter to 1/2, the resistance will increase 16-fold. And this reflects the fourth power dependence of resistance on the radius. Well, let's consider resistances that are arranged in series versus those arranged in parallel. Suppose we connect a group of tubes end to end, each of which offers a different resistance to flow. These resistances are said to be arranged in series. When you have resistances arranged in series, what is the total resistance offered by their combination? Well, there's one thing I know for sure, and that is, since the resistances are linked together in succession, the flow across each resistance must be identical. And the drop in pressure, the delta P, across each resistance must be the same. So the drop in pressure across the entire tube will be equal to the sum of each change in pressure. Since the flow across each resistance must be the same, we can divide each one of these pressure terms by Q, flow. Since pressure over flow equals resistance, we are left with this equation here. So for resistances in series, the total resistance offered to flow is simply the sum of individual resistances. Now let's consider resistances in parallel. Suppose we have 3 tubes which branch into channels with different resistances. So there are two things that I know for sure. First, the total flow across the three channels will be equal to the sum of the individual flows across each channel. And second, the pressure gradient that drives the flow across each channel will be identical for all three. So our knowns are that the total flow is equal to the sum of the individual flows, and that delta P, the driving force, must be identical across all three resistances. And since the pressure term is common to each of the three terms, we can divide each of the terms by the pressure. Since flow divided by pressure is equal to the inverse of resistance, the total resistance, expressed as an inverse, will be equal to the inverse resistances of the individual tubes. Let's take an example. Suppose these three resistances were 1, 5, and 10. If these resistances are arranged in series, the total resistance would simply be the sum of the individual resistances. 1 plus 5 plus 10 is equal to 16. On the other hand, if these same resistances are arranged in parallel, the total inverse resistance would be 1 plus 1/5 plus 1/10. Take the inverse of that and we get 0.7. So this shows us that it would take 21 times more pressure to maintain the same flow through the tubes in series as it would compared to the tubes in parallel. Okay, that concludes part 1 of this lesson. Take a short break and please return for part 2. Thank you.